Hello students, in today's class we shall discuss about the sign conventions. So in sign conventions we will consider that if a work is done by the system and if work is done on the system, if heat is absorbed by the system, heat is lost by the system, then what sign should be given to that particular quantity, means what should be the sign on W or on heat. So here we shall discuss about the sign convention. So in sign convention, the energy transferred as heat, if the energy is transferred as heat to a system from its surrounding, it is taken as positive. And if heat energy transferred as heat from the system to the surrounding, that will be taken as negative. So here from this chart you can easily understand what exactly going to happen. Here we have considered a system. Now if the heat is absorbed or gained by the system from the surrounding, then the value of Q will be positive. Q is the heat. And if it is given out, means the system is going to release heat, or heat is given off, or heat is lost by the system to the surrounding, then the value of Q will be negative. Likewise, if work is done on the system, means something is going to do the work on this system, this is the system, then the value of W will be positive. And if work is done by the system, then there will be negative sign before W. So these are the sign conventions, means when there is a work is done on the system, then the value of W will be positive. When work is done by the system, then the value of W will be negative. Likewise, heat is absorbed by the system, then the positive sign before Q. And you can say heat is given off or lost by the system, then the value of Q will be taken as negative. These are the sign conventions which are given by the IU Tech. So here next thing is internal energy, or we call it intrinsic energy. Basically this intrinsic or internal energy, it is made up of kinetic energy and potential energy of the constituent particles. So one can write U. U is the symbol for representing this internal energy, capital U. It is the sum of kinetic energy and potential energy, and that is what internal energy. Or we can say that this kinetic energy, the motion due to this kinetic energy, this is arises due to translational, rotational and vibrational energy. And similarly, the potential energy arises due to different types of interactions between the particles, like electronic energy, nuclear energy, energy due to molecular interactions, electronic energy. So these are the different types of interactions which are associated with the potential energy. And with the kinetic energy, we have the motion associated due to translational, rotational and vibrational energy. And in short, one can write that the internal energy, it is the sum of kinetic energy and potential energy. So one can write that internal energy is what? That is represented by capital letter U. It is the sum of all the forms of energy, whether it is translational, rotational, vibrational, electronic energy, bonding energy, right, stored within the substance or in a system, that is called internal energy or intrinsic energy. Now internal energy is a state function. It is a state function because the value of internal energy for a given substance is fixed and depends on temperature, pressure, volume, chemical nature and composition. Its value is fixed and that depends on the temperature, pressure, volume, chemical nature and composition. It depends upon the quantity of the substance contained in the system, and hence it is extensive property. Remember, extensive properties are those properties which depends upon the amount of substance. So internal energy, it depends upon the amount of the substance. That's why internal energy is an extensive property. We cannot determine the value of internal energy, means actual value of internal energy cannot be determined. However, we can only find out the change in internal energy. This delta represents the change in internal energy. Change in internal energy, that is delta U, accompanying a chemical or physical process is measurable. Means we can find out only the change and we cannot find out the internal energy alone, right? We can find out only the change in internal energy. Now, if we consider that the initial internal energy of a system is U1, 1 stands for the initial state, and the final internal energy, that is represented by the U2, 2 stands for the final state, right? Then the change in an internal energy, that will be given by final minus initial, means the internal energy of the final system to the internal energy of the initial system, that is delta U is equal to U2 minus U1. So here U is a state function. What does it means? Means that delta U, change in internal energy, depends only the initial and final state of the system, and it is independent of the path. Now internal energy is a function of temperature. Internal energy is a function of temperature. If there is no change in temperature, it means when the value of temperature is 0, means delta T is 0, change in temperature is 0, then definitely the value of del U, that is internal energy, will be 0, because internal energy is associated with temperature. If temperature will be high, then the internal energy will be high. If temperature, change in temperature is 0, then the internal energy will be 0. And because it is energy, so one can write the unit for internal energy is joule, and there is a relationship that 1 joule is equal to 10 raised to power 7 arcs. Now next, moving to the pressure volume work. Here you can see pressure volume work. It is work done when a gas expand or contract against external pressure. Here external pressure is taken in atmosphere. So it is the work done when gas expand or contract against external pressure. Here we have considered this is the cylinder fitted with the weightless and frictionless piston having area of cross section. You can see area of cross section A, and here this is the external pressure which is acting on the piston, and here we have taken 1 mole of a gas having the pressure Pi, initial volume Vi, and the pressure is P. So this is the initial state. Now what happens when the external pressure is little bit more than that of the internal pressure, right? Then the piston will move downward side. You can see piston will move downward direction. Here this is the VF, reduced volume having ideal gas having the internal pressure P, and this is the change in the volume, right? Distance covered by the piston from initial state to this is the final state, that is represented by the small change in the length, that is dl. So here let it contains a 1 mole of a gas having volume Vi in the initial state we have discussed. Pressure of the gas inside is P. P is the pressure, inside pressure or the internal pressure of the gas. Let external pressure acting on the piston is P external. If P external is greater, slightly greater than the internal pressure, then the piston is moved downward till pressure inside the cylinder becomes equal to P external. Means here piston will move downward till the pressure inside the cylinder will become equal to P external. Let this change be achieved in a single step and final volume will be VF. Here you can see the final volume is VF, and this change is going to happen in single step. From this state, this is the initial state and this is the final state, because we have considered that external pressure is slightly greater than the internal pressure. Then the final volume is, here we are getting VF. During the compression, you can see here compression is going to take place because P external is greater. During compression, let the piston moves a very small distance L. The change in the volume is given by, change in volume that is given by L into A. A is area of cross section, N is the length. So one can find change in volume, that is del V is equal to V final minus V initial, that is equal to L into A. And we know that pressure is force per unit area. If you cross multiply it, one can get force is equal to pressure into area. Therefore, from force on the piston, which is going to take place on the piston, that force is equal to P external into area of cross section, means F is equal to P external into A, and A is what? Area of cross section here. Now if W is work done on the system, by the movement of the piston, work done on the system, then work done is equal to force into distance. Force, we have calculated the value P external into A. Distance is small distance, that is dl. And as we know that area into length is what? Volume. So one can write area into volume, one can write delta V. And here we have written here minus sign. This negative sign is necessary here to give the conventional sign of W, because here work done on the system, then the value of work done will be positive. So here we have taken negative sign, because in order to satisfy the sign convention, because work done on the system, that will be positive. And we know that P external, that comes out to be, after multiplying it, P external del V, and here W is equal to minus P external VF minus VI. Here VF is the final volume and VI is the initial volume, and here because external pressure is greater, that's why the gas is going to compress. So here VF, the value of VF in the compression, VF is less than that of VI. Initial volume will be higher than that of the final volume. That's why here the change in volume V final minus V initial, that will be negative. And you know, negative multiplied by negative, here this is negative value, and here negative sign is there, negative multiplied by negative, that will be positive. That's why here we have taken negative sign, because this will fulfill that work done on the system as per the sign convention. However, if P external is less than P, then the gas will expand, reverse of the case. Then work will be done by the system on the surrounding. Here VF will be greater than VI, so change in final minus initial, that will be positive, and one can get W is equal to minus P external del V, and from here the work done will be negative, because here the gas is going to expand. So we have the relationship that if gas contracts, final volume will be lower than that of the initial volume. If gas expands, final volume will be greater than that of the initial volume. If there is no change in volume, then the final volume will be equal to initial volume, no change in the volume. Here change in volume will be negative, here change in volume will be positive, and here change in volume will be zero, because both the volumes are same, right? So work done on the system, you will see that value will be positive for W. Work done by the system, in that if when the gas will expand, then the value of W will be negative, and if there is no expansion, no contraction, then the work done will be zero here. Next, moving to, now let us suppose that pressure is not constant at every stage of compression. Compression when P external is greater than P internal, but changes in number of finite steps. Then what we will do? Then the work done on the gas will be summed over the all steps and will be equal to, here we have taken the summation, right? So here W is equal to minus summation P external del V. Here we have considered in the pressure, we have taken the pressure volume graph. Here pressure is not constant, right? Again here we have taken pressure volume graph. Here pressure is not constant, means pressure is going to change. You can see pressure is going to change along y-axis. Changes in finite step during compression. Changes in finite, we have the finite step. You can see this is the finite step, this is next finite, this is next finite. We have to find out the work done just by adding all these. That's why we have taken the summation here, right? Because we have to take the overall work done. So we have to add this pressure and change in volume, right? Here initial volume, when the gas is going to compress, then this is the final volume, right? But here in this case we are taking that changes in the infinite step, means this is a reversible process during the compression from Vi to Vf. This is the initial state, and this is going to compress. You can say when the volume is going to decrease, the pressure is going to increase as per the Boyle's law concept. So here we will get that the work done on the gas will be summed over all the step and will be equal to W is equal to minus summation, because we have to add all these steps, and then we will find out the overall work done, and this is represented in by the graph A, and this is for reversible condition. This graph is for reversible condition. Next, moving to work done in isothermal and reversible expansion of an ideal gas. Now here we have considered volume of the system changes by the infinite quantity Vi to Vf from initial volume to final volume. Then the total work done W on the system can be obtained by integrating PdV. When pressure is constant, we have taken this W irreversible is equal to minus P del V. But in case of reversible system, we have to integrate over the volume changes from initial to final, right? So one can write W reversible is equal to minus integrate from initial volume to final volume P external into dV. Further, we know that during reversible process, P external is equal to P internal plus minus dP, change in the pressure, right? If there is a expansion, then the pressure will be plus dP, and if there is a compression, then there will be minus dP. So overall one can write P external is equal to P internal plus minus dP. For reversible work done, one have to integrate over the limit Vi to Vf. So one can write P in place of P internal, P external, one can write P internal plus minus dP, because dP, if we multiply it, dP and dV, these are very, very small, so we can neglect it. So one can write that it comes out to be P external, that is equal to P external. So this one can write only equation 1, that for reversible work done it is equal to minus Vi to Vf limit P external into dV. For an ideal gas, we know that PV is equal to nRT. From here one can write P is equal to nRT by V. Putting this in equation 1, put the value of P external, this is P external in here. So one can get W reversible is equal to minus integration Vi to Vf nRT by V into dV. And we know that this n number of moles of gas, R is the universal gas constant, T is the absolute temperature, right? These are the constants, so we have taken it outside the integration, right? So we are left with 1 into dV. Integration of this, that is equal to natural log of volume. So one can write ln V, and just by putting the limit from higher to lower, Vf minus Vi. So this is the logarithm formula. One can get ln V final by V initial. So we have to now change natural log into log base 10. So we have to multiply it by the factor 2.303. Then W reversible, that comes out to be 2.303 nRT log Vf final volume divided by initial volume, right? So this is the work done for the reversible system. And now at constant temperature, right? At constant temperature, we know according to Boyle's law, PV is equal to constant. So one can write Pi Vi is equal to Pf Vf, or one can write Vf by Vi, rearranging them, that comes out to be Pi Pf. So in place of Vf by Vi, one can write Pi by Pf. So here one can write in terms of pressure, W reversible is equal to minus 2.303 nRT log Pi by Pf. So dear student, in this class we have discussed about how one can find out the work done and for reversible and irreversible process, and these are the mathematical relationship you can see, and these are very important for your numerical point of view. So you have to understand these concepts. So thank you very much for watching it. Have a great day.